With us here is Dr Peter Hopcroft of the University of Bristol's School of Geographical Sciences and Cabot Institute. He's a climate scientist and has just published a paper in Nature Communications called Understanding the Glacial Methane Cycle. So Peter, can you start off by giving us an introduction to yourself? How did you get into climate science?
So I have a physics background, but I've always been interested in how the environment changes around us, and ever since I was younger, I was interested in potential changes in future climate, rising sea levels and so on that I heard about.
So let's just start off by working out how our climate is affected by gas emissions.
So emissions of greenhouse gases contribute to the levels of things like carbon dioxide and methane in the atmosphere. These are called greenhouse gases because they absorb infrared radiation, and so they trap heat close to the surface of the planet, and as you change the levels of those greenhouse gas in the atmosphere, you can trap more or less heat and thus change the temperature of our climate, so warm the surface or cool it.
And does that have a positive feedback cycle? The more gases causing a greenhouse effect, I don't know.
So it's probably an open question, and you have to separate different contributions of those greenhouse gases, so the man-made sources and the natural sources, and whether or not they constitute a strong or a weak feedback isn't really fully understood yet.
So of all the gases that can cause a greenhouse effect or cause global warming, which are the worst culprits?
So in terms of man-made contributions, the most important greenhouse gas is carbon dioxide, which we've all heard about. It's probably responsible for about 2/3 of the man-made global warming forcing potential since before the Industrial Revolution. And the second most important greenhouse gas is methane, which is responsible for about 20%. And there are a variety of other gases that are emitted by human activities like nitrous oxide and CFCs that you might have heard about.
So how do we actually measure the amount of these gases in the atmosphere?
So for carbon dioxide, we've been measuring, or scientists have been measuring the concentration in the atmosphere at a site in Hawaii at Mauna Loa since the late 50s. And that gives us a sort of continuous high-frequency record of how carbon dioxide varies and how it's been increasing since then. For methane, we have a slightly shorter record that only goes back to around the 1980s. Before that, we have a kind of natural archive of these gases in the form of bubbles of air that get trapped in snow, which layers up in places like Antarctica and Greenland. And icicle scientists have analyzed those bubbles and use that to reconstruct how those greenhouse gases are varied on really long timescales, going back to nearly 800,000 years. And so we can see natural cycles in those greenhouse gases, and then the recent increase due to human activities, which goes way beyond the natural range for both carbon dioxide and methane.
So you've looked at methane in particular. Why just study that one gas?
You could argue that methane is slightly less well understood than carbon dioxide in terms of the global cycle. It's also quite an interesting gas for a few reasons. It has a short lifetime in the atmosphere of about 10 years, which means that if you change the sources now, then the impact in the atmosphere is quite rapid. It's on a decadal timescale. So you could, in the future, you could quickly reduce man-made forcing of climate change by reducing methane in the atmosphere. It's also got quite an interesting long-term, from a long-term perspective, it's quite interesting because if you look back over thousands of years, you see quite interesting fluctuations that are sometimes rapid and sometimes slow.
So if we look at the amount of methane that's been put into the atmosphere over a relatively short timescale since the Industrial Revolution, we've seen an absolute massive increase. But you've been studying what happened before this time. Why is that important?
So methane's increased from about 700 parts per billion volume before the Industrial Revolution to about 1,800 parts per billion volume today. And we understand pretty well that that's due to human activities, but there's also a natural component in the methane cycle, and that could have contributed some of this increase and could contribute further changes in the future. So if we look before industrialization, we can look at how the natural methane cycle varies in response to changing climate, changing weather patterns, and so on. And if we get a better understanding on that, we can have less uncertainty about how the methane cycle is varying now and possibly in the future.
So what kinds of natural sources and sinks of methane are there?
So probably the prime source of methane is from wetlands, so bacteria in saturated, so very waterlogged soils decompose plant matter and organic matter and release methane. There's also a variety of other sources, so things like termites, wildfires, there's emissions from geological sources, and even the oceans. The main process by which methane is removed from the atmosphere is a chemical reaction with hydroxyl, and there's also a sort of secondary, smaller sink from reaction with chlorine in the atmosphere, and it's also consumed by bacteria in dry soils. And so overall, there's quite a range of different sources and sink processes that control how much methane there is in the atmosphere at a given time.
So, having compared these sources and sinks, what have you been able to say about the methane cycle before the Industrial Revolution?
So we looked at the methane cycle in two time periods. The last glacial maximum, which is during the last ice age, and the pre-industrial, which is just before the Industrial Revolution. Now, we know from ice core records that atmospheric methane was very low during the ice age, and that its abundance in the atmosphere pretty much doubled by the time of the onset of industrialization. So we used an Earth system model, which is a numerical computer model, to try and predict or reproduce that increase between those two time periods. And so we attempted to build in a global picture of each of the different sources and each of those different sink processes that we mentioned before. We found that the sinks in the two time periods gave roughly consistent lifetimes in the atmosphere of methane, which means that the doubling of methane in the atmosphere had to be caused by a doubling or more than a doubling in the strength of the sources. And we think that tropical or wetlands in equatorial regions were the most important factor for that.
So I guess it's kind of logical that as the Earth warmed up and the ice melted, that more wetlands formed across the planet.
So there's a couple of different factors we had to consider. As the climate warmed, that increases the activity of these bacteria that produce methane in wetlands. Weather patterns also change, so the distribution of rainfall and thus the distribution of wet soils changed. But also the amount of land that was exposed changed. So as the sea levels rose after the ice age, some of the land that could be wetlands was submerged and was no longer contributing. And then finally, the other greenhouse gas that we talked about earlier, carbon dioxide, also rose quite significantly between the ice age and the pre-industrial. And carbon dioxide has an effect on plants, and it's called CO2 fertilization. And that also affects how much of that plant matter there is available for methane production in wetlands. So it's kind of quite a complicated picture of different, sometimes opposing effects that we had to consider.
It does sound like a very complicated model. Did you have quite a time putting it together?
So we ended up adding a lot of different components together to produce this overall picture of the methane cycle, and we used a lot of time on a high performance computer.
So what are the implications of this study? Are we able to infer anything about possible methane emissions in the future?
So it's difficult to draw direct conclusions about future methane change from our study. But what we did find is that our models of the source of methane were actually unable to reproduce the full amplitude of the methane increase between the Ice Age and the pre-industrial. And so that makes us cautious of applying the same models of methane sources from wetlands in particular into the future. And we think more work needs to be done to fully understand that discrepancy that we found. But in terms of the future climate, as the climate warms and weather patterns shift, that could have an effect on the natural methane cycle in the future, and that could act to increase methane in the atmosphere and thus act as a positive feedback on global warming, but we don't know how strong that feedback is.
Should we therefore be targeting methane in an attempt to slow down global warming?
So because methane has a short lifetime in the atmosphere, any change we make in the sources of methane now will have quite a rapid effect in the atmosphere. So if we suddenly tomorrow stopped all man-made emissions of methane, then that could have quite a rapid impact. But obviously there's also carbon dioxide to consider, which causes the majority of the greenhouse effect at the moment.
So what do you feel the take-home message of this article is?
So one consideration that comes out of this study is to keep a focus on not just man-made emissions of methane, but also natural sources of methane, because those natural sources can be themselves strongly influenced by ongoing changes in climate due to global warming.
All right, Peter, thank you very much for joining us.
Thank you.